by C, B by C, with the condition the greatest common divisor of A and B is equal to 1. Then the statement says A times B divides C. This is the one that you want to prove. And to convert this into our addition, subtraction, multiplication language, we use this statement. A divides C can be converted to C equals A multiplied by some number such as K, and then C equals B multiplied by some number such as L, and then the goal is showing C equals AB multiplied by some number. So this is the goal. And why do we need these things? Because if we use just description, it is abstract, but if we use equals or addition, then it's easier, right? Using equals is easier. And also, we can convert this to this one by the statement or theorem that I mentioned. So this is not easy to handle directly, but this is better, right? This is better. So up to this point, I covered. And any questions up to this point? Then using this, I want to achieve the goal. And last time I had a hard time, but the reason was underloading. So let's overload it this time. Instead of just writing less letters, writing many letters. C equals C times 1, and then C times 1, and then 1 is given here, AX plus BY, right? And CAX plus CBY, and then now C equals BL. Do you follow me? And this C is AK. So we overload and then write as many letters as possible. Last time I tried the opposite way and I failed. So we changed the direction. I overload. And after overloading, we have enough ABs, right? So we can extract AB. After extracting A and B, we have LX. After extracting A and B, we have KY. And all the involved letters are numbers, right? All the involved letters are integers, integers. So all integers up to this point. So I showed that C is equal to AB multiplied by some integer, right? Integer plus integer, so integer. So because of this reason, we can say that AB divides C. So underloading isn't very helpful. You should overload. Instead of simplifying it, you make it big, right? One doesn't look very big, but once you write many letters, then it's big. Then from this big thing, we can extract something. Any questions? Then the next thing I want to prove is corollary theorem 2.5 called Euclid lemma. But if you have a question, you can stop me. You can ask a question. Theorem 2.5. 2.5, sometimes called Euclid lemma. And the statement says, if A divides B multiplied by C, then, of course, with the condition, GCD equals 1, right? With this condition, then A must divide C. In other words, A divides B multiplied by C, but A does not divide B because of this condition. Then A must divide C. This is the statement. So let's prove it let's begin the proof by converting this statement into equals, right? Equals representation. So first line can be written in this form. BC equals A multiplied by some number, say K. And here, GCD, AB equals 1, it can be converted to what? AX plus BY equals 1. And finally, what is the goal? Goal is showing that C equals A multiplied by something, right? So we have this goal. So let's not underload, let's overload. So to do it, what I want to do is writing these things using the representation C equals C times 1, right? And then C equals 1 equals, I overload, right? Instead of using simple one, I use complicated one, A, B, Y. Do you follow me or not? Because if we underload like I did last time, then we cannot extract very many things. But if we overload, right, then we make many letters, then we may extract something from many letter expression, right? Do you follow me or not? So the key is overloading. Then after this, from this overloaded thing, we want to extract something. The goal is extracting A. Fortunately, we already have A. So we can extract A and then remainder, right? And then C, B, Y. We couldn't extract A here, but we can get help from the condition. What is BC? BC is what? AK. So BC equals AK. Then we can extract A. So after these things, we can extract A. Then it is CX plus A is extracted and KY. All the involved letters are integers, right? All the involved letters are integers. So we achieve the goal. So because of this, we have proved this thing, right? We have proved this thing. Done. So the key on both problems is making simple thing, converting simple thing into big thing, right? Into big thing. One is very simple, but do not use one, because you use simple thing, how can you extract some kind of letter, right? Some specific letter. It's tough. So you overload, right? Then you have many things here. And you may extract something. So here we extract A. There is no A. So we use this relation to extract one more A. Then A and A are extracted. So this is the key. So it's very similar to previous problem. Then let's prove the case covered in Euclidean algorithm. So let's go to the Euclidean algorithm section. And the key thing that I mentioned was this one. What is the division algorithm? If you divide A by B, then there should be quotient Q and the remainder. So this is the division algorithm. And from this division algorithm, we could derive Euclidean algorithm. But the key part was not proved. We only used Euclidean algorithm to calculate the result. But the key portion was not proved. What was the key portion? The key leading to the Euclidean algorithm is this thing. GCD of AB, the greatest common divisor of A and B, is equal to the greatest common divisor of B and R. This is the key leading to the Euclidean algorithm. If this is not true, then Euclidean algorithm would not work, right? Do you follow me? So last time I showed you the technique. This time I proved this key part leading to Euclidean algorithm. So let's do it. So GCD of AB is equal to GCD of BR. First of all, I don't want to write down 1, 2, 3, 4, 5 letters and then parenthesis, comma, and parenthesis. Total 8 times I should write it. So instead of using this thing, I will call this side G, right? G represent the GCD of A and B. So let's do it. So I want to prove this statement saying GCD of A and B is the same as GCD of B and R. First of all, G is the GCD of A and B, so G should divide both A and B, right? G should divide both A and B. Do you follow me? GCD, greatest common divisor of A and B, means it's a divisor of A and divisor of B. So G should divide both A and B. Then, can you solve this linear equation for R? What is R? If you solve this for R, R is what? A minus BQ. Right? And as you can see, I will make it rigorous. G divides A and B can be converted to equality language. If we use equality language, G divides A is converted to A equals what? G times some number such as K. And if we convert this into equality language, B equals G times L. Do you follow me? I used this technique over and over again. The key is the conversion. So with these things, I rewrite it. Equals A GK, right? A is GK, and then B is GL, Q. Do you find the common factor here? Do you find the common factor here? What is the common factor? G is the common factor. Then K minus L, Q, L. All the characters are integers, right? All the characters are integers. Because of this reason, if I convert this back to R language, what is it? This says what? G divides R. In other words, GCD of A and B is a divisor of R. So, take a look. If I combine all the result, then G divides A, B, R, right? G divides A, B, and then R. All these numbers are divided by G. So G is a common divisor of B and R. Any questions up to this point or not? Then I will challenge you. Is this enough, or do we need to do something to make it complete? So what should we do? Can you stop here, or we should do something to finish the proof? So what is your opinion?
We don't know if it's the biggest.
That's the key, right? Greatest common divisor. This shows that G is a common divisor of B and R. But can there be bigger number than G dividing both B and R? That is the question, right? That is the question. So, if you are asked to prove this thing and stop here, you may get partial credit, but not full credit, because you didn't show the other part, right? The greatest part, right? The greatest common divisor. You showed that it's a CD, but not GCD. Do you follow me? So the next part will be shown. So I will point this out. Initially we start off with AB, right? It's divided by GCD, right? Then we included R, so now everything is divided by G. So we say G divides both B and R, or in symbolic notation, we show that G divides B and R, right? So it's just rewriting using symbols, right? Then the next part is showing that G should be the greatest. In other words, there couldn't be anything bigger than G. Or, more technically, if there is any CD of B and R, that C should be less than or equal to G. Do you know what I mean? So this is the strategy. Strategy is this, idea is this. If C divides both B and R, then C cannot exceed G. This is the one that I want to know, right? Do you follow me? Right? So initially I showed that G is a divisor of both numbers. But that's not enough, because there could be bigger number dividing both. So to prove that it should be the greatest, I assume generic C. Assume that there is any C dividing both B and R. Then this C cannot exceed G. Then the end of the story, right? So this kind of thing is the key part in the proof. So let's prove it. C is a divisor of B and R. Then what I want to do is, C is a divisor of A, B, R by almost the same technique. Do you follow me? If C is a divisor of B and R, then C is a divisor of B, A, R. I didn't show this yet, but I'm mentioning about the idea. Then this means C is a divisor of A and B. So in other words, C is a common divisor of A and B. But what is the greatest common divisor of A and B? By definition, G. So C is a common divisor of A and B, but by definition, G is the greatest, so C cannot exceed G. Done, right? So only thing remaining is just filling the gaps, right? So you have the idea first and then fill the gap. So take a look. Assume that some number divides both B and R, then it's a CD, not GCD. And I want to prove that C is less than or equal to G, and I did it. How? If C divides B and R, by almost the same idea, C should divide every number, right? That means C should divide A and B, then C is a CD of AB. But the greatest CD of AB is what? G. Because of this condition, C cannot exceed G. If C exceeds G, then the greatest common divisor of AB is C, not G, or some number bigger than C, right? So I completely explained the idea, except the detail. So the only detail that is missing is showing this. And this follows almost the same path as this thing. So please fill this gap. Please fill this gap by following this idea. Then you can practice. So I will give you 1 minute to fill this gap. From G dividing B and R, you lead to G divide A. Then you are done. Almost the same technique. Only thing is the change, like switching A and B and with plus, then essentially identical. I don't want to write down. If you have difficulties, then I will write down. But if you can handle it, then I will just describe. So I showed that if C divides B and R, then C should divide A. That means C should divide everything A, B, R. Any questions? So exactly the same as the previous thing, except the change of letters and signs, right? Addition or subtraction, that kind of change. Then now we can use these things to prove the Euclidean algorithm, and roughly this is the idea. We have A and B given by the problem. A is, for instance, any number, 1,000,010 or 1,000,011. B is 1,000,000,011, right? Or vice versa. So B is 1,000,000,011. I mean, A is 1,000,011, B is 1,000,011, right? So there are two numbers. Then finding the GCD is very difficult. So what you do is divide A by B. 1,000,011 is divided by 1,000,011. Then there is quotient, right? Almost 1,000, right? Plus the remainder. Then as you can see, A is 1,000,000,000 at least, greater than a trillion, but R is between 0 and 1,000,011, right? Do you follow me or not? In other words, instead of worrying about big number, we can handle manageable number. But now, we apply the same thing to this B and then R, right? We apply this to B and R. So instead of calling this using many different letters, I will make uniform description. Instead of ad hoc description, I will make uniform description. To do it, I will call this R0, R0, and I will call this R1. Then I can make uniform description. So because I call this R0, this could be called R0. Instead of B is R0, and I can write it this way. Do you follow me? So A, B, GCD is R0, R1, GCD, and then R0, R1, GCD is R1, R2, GCD. Similarly, R1, R2, GCD is equal to R2, R3, GCD by the same reasoning, but if you don't follow me, let me know. Then R, for instance, N minus 1 equals R, N, Q, N, and then Rn plus 1, right? Each time, this Ri is in between, right? Ri is between two numbers, 0 and the top number. So we can create this kind of thing, and then it cannot continue forever because we begin with a finite number A and B, right? Finite number divided by a finite number, then the remainder is bounded, right? So this step is not infinite. This step stops somewhere, right? And eventually, we will get the number such as 1, right? 1 somewhere, or 0 in the, so we will get either 1 here or 0 somewhere, right? We will get these kind of things in the end. Or some number, we can stop. In other words, we can have 0 at this position. So let's call that position nth position. So this will happen. After some steps, R capital N, Q capital N plus 0, and R capital N minus 1. So somewhere, this will happen. It cannot continue forever. Somewhere it should become 0. In other words, the GCD of Rn and R minus Rn and R sub n minus 1 is, in this case, what? R sub n. So this will happen. Do you follow me or not? So this is the Euclidean algorithm written theoretically. But what is the key theory? The key theory is this. The GCD of these two numbers is the GCD of these two numbers, right? And the GCD of these two numbers R0, R1, the GCD of these two numbers R0, R1 is the GCD of R1, R2. Do you follow me? And the GCD of R1, R2, right? The GCD of R1, R2 is the GCD of R2, R3. And you can continue. And the GCD of Rn minus 1 and Rn is the GCD of Rn plus 1. And then eventually GCD of the previous thing, or GCD of this thing, is the GCD of this one and this one. But anything, GCD of anything and 0 is anything, right? The number. So as you can see, the GCD is this number. This is the key idea behind the Euclidean algorithm. I already showed you how to find it, but now you have theoretical backup, right? So with theoretical proof, you have confidence in using the Euclidean algorithm. So I will pause and you may check. So what I did was using best stacking method. When you use division algorithm like elementary school idea, then it doesn't stack well, right? A divided by B equals the quotient and the remainder. Then after this, it's very difficult to stack, right? Just this is the end of the story. So this stacking is not great. And the other stacking, like theoretical stacking, is good enough, but it's not very practical. So the best thing is stacking it differently. A and B, right? A and B are positioned this way, and then Q is positioned here, right? Q is positioned here, and then the remainder is positioned here, right? I might write the wrong thing. This is wrong. B, right? B times Q should be subtracted. And this, and I call this R, right? I call this R. So I use this stacking method, then we can repeat, right? We can repeat the stacking. So I will do it one more time. A divided by B gives us the quotient Q and the remainder R. Then B divided by R gives us some quotient, right? Some quotient here, say quotient 1, right? Quotient 0, right? Quotient 1 and quotient 0. And then this is R0, right? So R1 and then R2. Do you follow me? So it's not a good idea to call this B. B is called R0 in the first place, right? B is the same as R0, right? So A divided by R0 gives the quotient Q0 and remainder R1. R0 divided by R1 gives the quotient Q1 and the remainder R2. R1 divided by R2 gives the quotient Q2 and the remainder R3. So we stack this way. Then it's not very tough and it's very systematic, right? So we use this stacking method. Some students might see these things in high schools or middle school or even elementary school. In any case, we write this way then. Eventually, Rn minus 1, right? Rn here, and Rn minus 1 divided by Rn equals Qn, and then the remainder could be 0, right? So we will see this thing in the end, right? It cannot continue forever. If it continues forever, then it means the numbers are infinite, but we didn't begin with infinite numbers, right? We began with some fixed finite numbers, so you cannot continue forever. You should stop somewhere in this form. Then we can read off this statement to get the GCD. So this is the GCD. So essentially GCD finding is very straightforward. So to test it, let's do it. Let's do it. Instead of just theoretical things, let's do it finite time. You may not see this thing anymore in this simple form. Of course, you will see complex forms adding the equality, but in this simple form, this is the finite time. So please pick two 3-digit numbers. Any 3-digit number is okay. So what is the first 3-digit number?
183.
And then second one? 600. No problem. 629. So let's find the GCD of these two numbers. So let's do it. What is the bigger number? 7, 8, 3 is the bigger number. So bigger number divided by smaller number gives us the quotient 1, right? If you divide this by this, then roughly 7 over 6, then it is roughly 1. Then the remainder is by subtraction. It is 4, and then 5, and then 1. Then if you divide 600 by 150, about the quotient is about 4, right? Quotient is about 4. Then 4 multiplied here, then 16. And then 4 multiplied here gives us 20. And then 4 multiplied 6, 16, right? So this is subtracted from this one, gives us 3, 1. Do you follow me? Just simple calculation. And I let you know how to calculate these kind of things using the algorithm. The next thing is finding the quotient. I want to divide 154 by 13. If you subtract 13 here, then we have 24. So it is 11, right? 11 multiplied by 13. So let's do 11 multiplied by 13. It's not very difficult, but I want to review what is the last time. 11 multiplied by 13 will be done here. 1 times 3 is 0, 3. 1 times 1 is 0, 1. 1 times 1 is 1, 0, 1, right? And then 1 times 3 is 0, 3. You don't even have to write down 0. Then 3, 4, 1, right? So 1, 1, 4, 3 is subtracted from this one with quotient 11. Then 1, 4, 3 subtracted is 1, 1. And then if we subtracted this thing, then the quotient is 1, and the remainder is 2. If we subtract this thing, quotient is 5, and the remainder is 1. And then if you divide 2 by 1, then it is 2, and the remainder is 0. So the GCD is 1. They are relatively prime. You chose two relatively prime numbers. So please browse these things and ask questions. No matter what numbers are chosen, these steps should stop somewhere, right? We cannot continue forever. So this is extremely important, believe it or not. Modern encryption, your cell phones have this routine embedded. So usually when we send signal, we convert the signal into ASCII code, and then ASCII code is converted, ASCII codes are combined to make some number, some big number, and then we scramble big number and then send it. Then if someone intercepts, they have some big number, but they cannot decode. Then how can the other party can really decode using this kind of routine? It's extremely fast. If you don't believe me, I will show you how fast you can calculate. So do you see Maple here? MATLAB converts the big number into exponential expression form. So I want to use Maple instead of MATLAB. Do you see Maple soft or something? Do you see it? MATLAB is here, but Maple, I will go to the front page to check it. But it doesn't matter. GCD calculator is embedded, and when we had Maple, I showed about 1,000 digit number and 1,000 digit number GCD, and then I pressed enter, immediately showed the GCD. Why? Because of this fast converging method. Take a look. We had very big numbers, right? But within a few steps, it become, right? These steps become simple just numbers, right? So it's extremely fast method. So this is the last time I'm showing you the simple version of GCD calculation. And as I mentioned before, it doesn't just stop here. It varies, right? It has variation. And then that variation is the key to the next section, 2.5 or 3.5, section 2.5 by 2.5. Then let's do it. And when I teach linear algebra or some courses, I always mention about the equality. When you have equality, what you can do is assume that these are equal, then we can add the same numbers, right? Or you can subtract same numbers, or you can multiply the same numbers. We can do the same thing to both sides. Do you follow me? Because it's equal. And assume that we have two equalities. Assume that we have two equalities. Then we can do anything to the top and anything to the bottom, and then do anything, right? Add, subtract. So as far as we have the equality, we can do anything, right? To both sides. The same thing to both sides. Because they are equal. This is a very important thing to understand the following thing. Assume that you have ax plus by equals c. And then assume that you have ab minus ab equals 0. Then we can do the same thing to both sides. Or we can add, subtract these two things. So let's add these two things. Then what happens? We add these two things. Ax plus a is extracted, right? B plus by minus a equals c. Do you follow me or not? Is it too complicated or not? It's just doing the same thing, right? And then adding equals, right? Adding the terms controlled by the equality symbols. If you don't understand this thing, ask me. This is very important in Diophantine equation. Then it's too trivial. I will tweak the problem. So instead of just this simple thing, I will tweak the problem. Can you multiply both sides? Can you multiply both sides of the second equation by some number, such as t, or not? Is it possible? Or can you divide both sides by some number, such as g? Is it possible? Then after doing this, if we add two equalities, what happens? If we add these two equalities after doing this, then what happens? What is it? What should come here?
Plus xt.
Right? This is what it meant, right? It's just doing the same thing, right? Oh, sorry, A. So we did the same thing to both sides and created this kind of thing. But if you don't understand, ask me. So what I did was this one. We had two equalities, and I can do anything to both sides, right? And then I can add or subtract two equalities. What I did was this one. From AB minus AB equals 0, simple equality, right? AB minus AB is 0, simple, right? I multiplied or divide, and then afterwards I added. Then I got this thing. If you think this is too tough, ask. Then let's do it. Assume that we have this kind of thing. I just pick any number, 1 to 3 equals 1 to 3 multiplied by 1, and then any number. So I will pick some number such as 96, right? 96 multiplied by what? 1 to 3 equals 1 to 3 times 1 plus 96 times what? 0. Similarly, 96 is 1 to 3 multiplied by 0 plus 96 multiplied by what? 1. Then, what is the key? We have two equalities. So we can do the same thing to both sides, right? For any case. But now, instead of doing just random things, let's use the previous stacking idea, following Euclidean algorithm. Then we can find the quotient. If you divide this by this, what is the quotient? Quotient is 1. Right? Quotient is 1. Do you follow me or not? I'm not just doing random things. I'm doing something that is controlled by Euclidean algorithm. So I got this thing. Then what is the remainder? If you divide 1 to 3 by 96, what is the remainder? 27 is the remainder. If you don't understand or don't follow, ask me. So up to this point is trivial. But now I want to apply the same algorithm to find the GCD. So if you divide 96 by 27, then what is the quotient? Roughly about 3 might be enough, right? Can 4 work? 4 will exceed 100, so 3 should work, right? Then 3 is the quotient. Then after subtracting 3 times this from the top portion, what do you get? 15, right? Of course, if you cannot do this calculation in head, then write it. I will do it here. 27 multiplied by 3, right? 27 multiplied by 3, then 21, right? 6, right? Then 1, 81, right? So 81 subtracted from 96, then 5, right? And then 1, right? So I got 50. So you can write these kind of things. As I mentioned on the exam, no calculators are allowed. So you need to do these kinds of calculations well. Then now, what will be the quotient? If 2 is too big, 2 will give us 30. 30 is too big. So it's good to use 1. Then if you subtract, then it is 12. Then the same thing. So 12, then 1, and then 3, and then 4, and then at last 0. 0 is the end of the story, right? 0 is the end of the story. Then what is the GCD? 3 is the GCD, right? So this is the Euclidean algorithm. But this is not the goal. Our goal is not finding our goal is finding the solution to this kind of problem. So I write the problem now. I just describe things. So problem is this. Problem is this. Find all solutions satisfying 1, 2, 3x plus 96y equals 3. This is the problem. Find all xy satisfying. This is the problem. Then suddenly, it's not trivial. The problem Euclidean algorithm itself is trivial, but the application solves non-trivial problem like this. This is the key. So let's do it. Then, as you can see, if you multiply 1 through, right? So I multiplied 1 through, right? Multiply 1 here, multiplied 1 here, multiplied 1 here. Then we get 96 on the left side. 0 times 1, 0. 1 times 1, 1, right? And then we subtract. Then this subtraction gives us 27. This subtraction gives us 1, 2, 3 multiplied by this subtraction, right? 1. And then this subtraction gives 96 multiplied by negative 1. If you don't understand, ask me. Now, we multiply 3 through. If you multiply 3 through, then we get 81 here. We get 81 here. We get 3 here. We get negative 3 here. Do you follow me or not? I multiply this number 3 through. Then I subtract this red number from the previous equation. So from this previous equality, I multiply this red number. Then what happens? If we subtract 81 from 96, we get 15, right? And then if we subtract then 1, 2, 3 multiplied by 0 minus 7 minus 3, so negative 3. Do you follow me or not? And then 96 multiplied by 1 minus negative 3, so 4. 1 minus negative 3, 4. And then multiply 1 through. So 1 is just to itself, so we don't have to write down anything. But now we subtract, right? If we subtract this equation, this equality from the top from this equality, then we get 12. We get 1, 2, 3, the same number, and then common factor, and then 1 minus negative 3, 4, and then 96, and then minus 1, minus 4, minus 5. If you don't understand, ask me. I am doing the same thing over and over and over again. Then do the same thing. I multiply 1 through and then subtract from the previous one. Then 1, 2, 3. And then this minus this one is negative 7. And then this minus this one is what? 9, right? 4 minus negative 5 is 9. Then this is it. What is x? Negative 7. What is y? 9. I found the solution. So trivial thing led us to non-trivial solution, right? So this is the key. Why do we study this number theory? Because we are learning very trivial things and stack it with proofs. Then we can use these things in high-tech devices. So please browse the idea and ask questions. Then you may think, oh, this is too tedious. So last time I showed you the abbreviation. Instead of writing down, take a look. Instead of writing down everything such as equals symbol, 1, 2, 3 appearing all the time, or 96 appearing all the time, plus appearing all the time. We just abbreviate. So I will write the abbreviation one more time, unless you have questions about this. So let's write the abbreviated version. Yes?
So the last 4 is not used at all?
4 is used to go to 0, right? So we can write one more equality.
It's the end, but we don't use it for finding the x and y, right?
Right, for finding x, so you don't use it. Once you see 0, you save one step. 4 is used to go to 0, and then if you do this thing, you will really get 0. But 0 equals something minus 0 is not very useful, so we don't go there, even it's possible. So it's not a matter of possibility, but it's the efficiency, right? So we stop here. We don't go down because we get some meaningful result. But meaningful result, we are just at 0, then it is not very meaningful in the end, right? So we stop here. Any other questions? Then let's write the abbreviated version. I don't want to write, so this is what I will do. I already showed you last time, but I had a plan to abbreviate. I don't want to carry carry these numbers all the way down. So I don't want to carry this number all the way down. So I will strike this out, right? I don't want to carry these numbers, or I don't want to carry these numbers either. I just assume that you have these things in your mind, right? I don't want to carry these numbers all the way down. And then I don't want to carry the signs, right? I don't want to carry these kind of signs or equalities. So I can remove many, many things to make this simple. But what is the trade-off? Once you remove these things and write down the simplified version, you may not know what is going on in the future. What are these? Just numbers. So always it's a good idea to keep the original version and then change it. So let's do it one more time. 1, 2, 3, 96. And then here, Euclidean algorithm first. Euclidean algorithm 1, and then 7, 2, and then 3, and then 15, 1, 12, and then 1, 3, 4, 0, right? This is the Euclidean algorithm, then this is the GCD. Then we now omit equal symbol, that big number, and we only write down 1, 0, 0, 1. Do you follow me? Then we do the same thing. Multiply this and subtract. Multiply this and subtract from the top, right? Multiply this and subtract. Multiply this and subtract from the top, from this portion, and multiply this and subtract. Multiply this and then subtract. Multiply this and then subtract. Multiply this and then subtract. Done. Suddenly something is written. But assume that you forgot to give the previous column and give this to your friend. Your friend may not have any idea about what is going on, right? It all came from very simple thing, equality handling. Take a look. The idea is nothing but just this very straightforward thing, right? Equalities, right? Equalities, add, subtract, do the same thing. Then we can just add anything, right? Then that idea is right here. So I will give you one more problem. One 20 and then 96, right? So please write the same table as the previous one for these two numbers with the abbreviated version, right? Do not write the full version. Done, right? What is the meaning of this? You should know the meaning. So I will write the meaning of the last line, not all the lines, but at least whenever anybody asks you, you should write down the meaning of this. This means 24 equals 120 multiplied by 1 plus 24 multiplied by negative 96. Multiplied by negative 1. This is the meaning, right? So once you see the line, it's not just the thing that you see. It's this. In linear algebra, you did this kind of thing, right? Did you remember that you do row echelon form calculation, elementary row reduction? You don't write down everything. You write down just numbers, right? And then continue.
Will you do this one more?
No problem. You may pick two numbers. So pick two numbers, then I will solve. Pick any two-digit number. The number less than 300. Pick two numbers that are less than 300. One number and one number.
138.
And then?
110.
Great. So we want to solve this problem. Then let's do it. 138, 110, then 1, and then 28, and then about 4 will work. May not work. 3 will work. 3 multiplied here, then 28 multiplied by 3, right? 28 multiplied by 3 gives us 24, and then 6. Then 484 subtracted from this one, then 6, and then 2. Then 1 gives us 2, and then the 13 gives us 0. So this is the GCD. So GCD can be written here. Any questions? And then I will write the right column. 1, 1, 0, 0, 1. Multiply and subtract. Multiply and subtract. Do you follow me? Multiply and then subtract. Multiply and then subtract. Multiply, subtract. Multiply, subtract. Done. 4 and negative 5 gives us. If you don't believe, calculate the result. I can do hand calculation, but to show this clearly, I will use MATLAB. So 138 multiplied by 4 plus 110 multiplied by negative 5 gives us 2. Right? Gives us 2. How did we get these numbers 4 and negative 5? Using the idea. Do you need more? If you need more, I can do more. Any of you need more, then I will do it.
Are there homework assignments that we do this in?
What do you mean by homework assignment?
Is part of our homework using these iterations?
If you are asked to,
I haven't looked over this.
if you are asked to solve this kind of problem, then what else would you use? Difficult, right? It's difficult. If you have other means, do it. I don't discourage you. You can do anything. As far as you get the solution, you can do anything. Yes?
What multiplied by what?
138 multiplied by 4 plus 110 multiplied by negative 5 gives us 2. So the meaning of this line is, will be written one more time. This could be the final time writing down the meaning. So this means, this column means, this row means, why am I? So this row means 2 equals 138 multiplied by 4 plus the other number 110 multiplied by negative 5, right? This is the meaning of this row, right? This row is just abbreviation, row abbreviation. If you use different method, I don't discourage you. You can use your own method or the method that you might obtain from other strategy. As far as you get the solution, it doesn't matter. Then the next thing is solving Diophantine equation of this type. Generally, how to solve ax plus by equals c. How can you solve this kind of thing? First of all, solution may not exist. So, solution may not, right? Solutions may not exist. So I want to exclude the bad case. You have a problem, but solutions may not exist. Then you wasted your time to solve the problem, right? So I want to exclude the bad case, and then after excluding the bad case, I will always assume that the solution exists. If GCD of A and B does not divide C, then solution does not exist. So I will make one sentence. Instead of 2 sentences, I will make 1 sentence. Just by doing this, right? Solution, Maynard is weak. Do not exist. Solutions do not exist if GCD of A and B does not divide C. In other words, C should be a multiple of the GCD. In other words, in the previous problem, if I asked you to find the solution, I will write down the same problem instead of going up. So example, if I asked you to find the solution like this, 138x plus 110 y equals 37. Then, can you find the solution? No way. Why? Because even number multiply something is even, right? Even number multiply any combination cannot get an odd number. Impossible, right? In other words, this should be a multiple of GCD. So we exclude this kind of case. In other words, we don't have to waste any time to consider this kind of problem having no solution. So from this point on, thus from this point on, we assume that GCD of A and B divides C, right? Assume that GCD of A and B divides the right side number, right? From this point on. Because if it doesn't divide, then there is no solution. So I will go up and continue unless you stop me. Then the next thing is this. Assume that you have found, so this is the problem itself, but you have found the solution, say 0, satisfying this thing, GCD, right? Once you arrive at the bottom, what you have found is this kind of equality, right? You have found the GCD, not C. Then what should you do? That's the question. What should you do? You are asked to find the number x0, y0, satisfying the above one, not the second line, right? What should you do? Because GCD should divide the C, we can multiply both sides by, we can multiply both sides C over G. That's all we need to do, right? We can do the same thing to both sides, right? So take a look. It's a simple fact. Add the same thing to both sides, right? Multiply the same thing to both sides. What I did was multiplying the same thing to both sides. Then what do you get? If you multiply these things, then you get A Cx0 over G plus B Cy0 over G equals C. Do you follow me? In other words, x equals Ax0 over G. Right, x equals Cx0 over G. So once you find the GCD, you are almost there, right? You are almost there. The only thing that you need to do is adjusting. By just adjusting, you can find the solution. So is it too tough or not? So let's change the previous problem. Assume that you are asked to find the solution to this problem. I don't know the answer to this one, but at least I know the answer to this one. Was it 4?
4.
So I do not know the answer to the above one, but I know the answer to this second line. Then what should you do? You adjust by doing what? The quotient, right? If you divide this by this, the quotient is what? 9. So you adjust by multiplying 9. So I multiply 9 here, multiply 9 here, multiply 9 here. Done, right? I did the same thing. I multiplied 9 everywhere. Then what is your answer? So answer is 36. Answer is negative 45, right? Then finally, I will describe, but I do not know whether we have enough time to fully study these things. But let me check. We can stop at 55 by this clock. Where is the clock? Here, right? Find all solutions. Find all, not just one. One, right? Do you understand the situation? Find all solutions, not just one solution. We know how to find one solution, but the question is not just one solution. Find all solutions. Then what should you do? In other words, find all solutions to this problem. Find all. You should not find a few. You should find all solutions satisfying this. Then I will write down the result first. 138, 36, 110, negative 45 equals 18, I know. Now this is the key. A and B are here, right? A and B are here. So I will multiply A and B. 138 minus 138 multiplied by negative 45, and then A and B, sorry. A is this 110, sorry. This is 110. 110. 110 equals 0. You understand this, right? Do you understand what I mean? You understand this thing. Now, I will multiply anything to both sides. So I multiply by t. Do you follow me or not? T is an integer, right? I multiply t. And then I divide by 2. That 2 is the common divisor of two numbers that we found, right? Do you completely understand what I did here? Why not? I multiplied both sides by t and divide both sides by 2, right? So I didn't change anything. In fact, if you subtract this thing from this thing, it's obviously 0. I didn't do very much, right? Just 0 is 0. This thing is 0.
Did you pick two randomly, or did you?
GCD.
Okay.
GCD. Then let's add two equalities. Then what happens? If we add two things, then 138 is the common factor, and then 36 plus this thing 110, t over 2 is 55t, right? And then this is 110 is the common factor, and then negative 45, and then 110 subtracted, then negative, this divided by 2, 69t. Or 18, right? 18. So I found all solutions, right? I found all solutions. This is it. So by small jump, right? By small steps, we could solve this complicated problem. Each step isn't very difficult, right? By small steps, we could solve this complicated problem. And next time, I will continue. So.
Also, if you filled out the last line that you were talking about, if you actually filled out that last line that equals 0,
Yes.
you could just add that to both sides and it would be the 50. You get 55 and 69, I think, on the last line.
No, that is also possible. That is also possible. Yes. But instead of relying on that too much, I just showed you because t is involved here, right? So you just attach t. So let's stop here, and next time I will continue. I will fully describe Diophantine equation of this pattern.